So good afternoon. Our speaker today is Jonathan Schiff. As a CV, he's got his undergraduate in physics at the University of Pennsylvania. Then he spent 1 year of research at Brookhaven National Laboratory studying quantum information. And now he's a fourth-year PhD student at the University of California in Santa Barbara. And he's an expert in cosmology, primordial magnetic field, recombination, and I guess all these topics are going to be together in his talk. Please, this is yours.
Thanks very much. Thanks for the kind introduction, and thanks for having me. Yep, my name's Jonathan. It's nice to meet everyone, albeit virtually. And I'm going to be telling you about my ongoing work with my advisor, Tasia, on primordial magnetic fields, modifications to the recombination history, and the implications of it all on the Hubble tension. So the plan is to introduce the Hubble tension, go over some basics, then go over some of the key features of recombination so that we can understand how we might reasonably modify primordial recombination, and then finally get into the way that primordial magnetic fields could reasonably change the basic picture here. So very brief introduction to the Hubble tension for those unfamiliar. It's a disagreement between late direct measurements of the present Hubble expansion rate h0 and early universe inferences from the statistics of the fluctuations in the CMB. Now, the late universe measurements rely on something called the cosmic distance ladder, in which you use initially a geometric calibration of some standard candles. Those are used to calibrate standard candles at further distances. Then from, in the simplest case, just thinking about the linear Hubble relationship, knowing the redshift and the distance to these standard candles, you can measure h0 with different techniques in this distance ladder, actually now giving slightly discrepant results, but what I think would still be considered the state of the art from the Schiff collaboration, giving 73 plus or minus 1 kilometer per second per megaparsec. The early universe measurement is, unlike the late universe one, is very much cosmology model dependent, and it's a bit involved. So I just want to spend a bit of time going through how it works. It relies on the fact that we have this, one of the most precisely measured quantities in cosmology, the angular scale of the BAO peaks in the CMB's temperature power spectrum, which is given by the ratio of the co-moving sound horizon to the surface of last at the time of the CMB's release over the angular diameter distance to the surface of last scattering. So the idea here is if I can, from first principles, compute the co-moving sound horizon at the time of CMB's release, and then I have some cosmological model for the energy content post-recombination, then the only leftover free parameter here would be h0, and then from this ratio, the measured value of theta s, I could infer the value of h0 with a Planck 18 best fit results giving 67 plus or minus a half, standing in more than 5 sigma disagreement with the Schiff result. The strategies that you would go about in order to try to resolve these two, if you trust this late universe measurement, is gonna be basically all the same. Change something in this ratio so that the only way to keep it fixed to the observed value of the angular scale of the BAO is by compensating with an increase in h0. So the ways that people go about this fall broadly into two camps. You can change pre-recombination or early universe physics by changing something in the numerator in the computation of the co-moving sound horizon, or something post-recombination with a late universe result, chiefly through changing the energy content after recombination. Early universe approaches, which is what I'll focus on here, all seek to do the same thing. They seek to shrink the co-moving sound horizon at the time of the CMB's release, because then you would have to shrink the denominator too, which is inversely proportional to h0, and the hope is that you'd bring up the value of h0 closer to the late universe measurement. People consider different ways of even trying to shrink the co-moving sound horizon. Probably the most popular one is changing the expansion history prior to the time of the CMB's release by introducing something like early dark energy. But what we'll be considering here is whether an earlier recombination, so that changes Z star, just changes the integration bounds here, an earlier recombination shrinks the integration bounds, that also would shrink the co-moving sound horizon and hopefully help alleviate the Hubble tension. Okay, so with that, now I just wanted to spend some time on some background on recombination, and I won't go into too much detail. I'll just try to highlight the key features. And the first aspect of note is that all models of recombination in the standard picture, even as you move up in levels of sophistication, suppose it's a local process. It's set by basically just the local conditions in any patch, primarily the local baryon density field. And that's true even from the simplest models like Sala, which is just given from local thermodynamic equilibrium, to the Peebles three-level atom, first worked out by James Peebles and Zildovich in the 60s, which is a effective yet very accurate model for recombination. And then even state-of-the-art codes like HIREC, all of those suppose it's a local process. A bit of how we understand recombination to work. The Saha model is imagining you have, again, just from local thermodynamic equilibrium, direct recombination from an ionized state to the ground state. It turns out recombination doesn't work that way because the mean free path of photoionizing photon is so short that you have detailed balance between direct recombination and immediate subsequent photoionization. So instead, the way recombination primarily works in the early universe is you first recombine to some excited state, you gradually relax to the n=2 state, and then finally you can have a successful recombination to the ground state from the 2s state via 2-photon emission, or from the 2p state because Lyman-alpha photon gets redshifted out of resonance. On the left here, I'm showing you the ionization fraction as a function of redshift. So this is the ratio of the free electron number density to hydrogen atoms. At early times when the universe is fully ionized, this will be 1, or actually slightly bigger than 1 when you account for helium, but let's not worry about that. Then recombination begins and this falls, and recombination is said to happen at around redshift of 1100. You can see Saha does a decent job of estimating the onset of recombination, but then overshoots the rate. You also can't see it here, but it misses the freeze out due to the expansion. But you can see that the three-level atom, despite being pretty simplistic, does a very good job of capturing the correct recombination history compared to the even state-of-the-art codes. And so that'll be kind of our working model for recombination throughout here. Okay, the only really technical part of recombination, well, one of the key technical parts of recombination that I want to mention here as well is because it's a two-body process, a proton and electron coming together, the recombination rate, here thinking in terms of the free electron number density, depends non-linearly, depends quadratically on the local electron number density or as well on the local baryon density field. And that means that if I introduce inhomogeneities, not only will overdense regions recombine faster and underdense regions recombine slower, but I have some no net shift to the average recombination rate. Because of this nonlinear dependence, if I then take a spatial average by virtue of Jensen's inequality, I end up with an overall speed up. So the name of the game here is if we want to introduce something that's going to speed up recombination, I need to introduce yet unaccounted for inhomogeneities in the baryon density field beyond the standard ones that we have in the context of Lambda-CDM and adiabatic primordial fluctuations that could lead to a speed up in the background recombination rate. One feature of the CMB's power spectrum that I forgot to mention is here what's referred to as the diffusive or silk damping tail, and that is that if you go to higher multiples or smaller and smaller scales, in standard Lambda-CDM, where you have no additional driving term, on very small scales, if you can imagine if I have a hot spot and a nearby cold spot, I would just have photons diffusing over and smoothing out any of those fluctuations. So if we want to introduce new inhomogeneities that aren't already accounted for, that aren't constrained, we would need something to source well into the diffusive damping tail, where in the standard picture, all of the power has been exponentially suppressed. But now there's this new source that's not already directly constrained from CMB instruments that's giving us excess power and leading up to the speed up in recombination. So about 10 years ago, it was realized by Karsten Jadamczyk and Tom Adel that primordial magnetic fields are a really natural source for this small scale clumping, that realistic primordial magnetic field strengths that people consider that aren't directly constrained already would naturally source baryon clumping very far into this diffusive damping tail, where you would typically expect to have no excess power. Initially, the way people went about, though, trying to test how this modifies the recombination history was very simplistic. They kind of leveraged the local recombination assumption to partition the universe into regions of overdensity and underdensity or background mean density, ran standard recombination codes modified to the local conditions in any patch, and then took a volume weighted average to see for a given clumping ratio that for the baryons that you would expect from primordial magnetic fields, how that might modify the recombination history. That's inadequate for a whole host of reasons, but one that I want to focus on here is that on the small scales at which these primordial magnetic fields will naturally source the baryon clumping, the local recombination assumption breaks down. And to understand why that is, you can imagine if I have an overdense region that's recombining faster and a nearby underdense region, and if I'm on a really small scale, as well below the mean free path of a Lyman-alpha photon, then I have that successful recombinations in the overdense region can allow Lyman-alpha photons to escape and diffuse out to a nearby underdense region, which would lead to more successful recombinations in the overdense region where recombination is happening fastest, and then inhibiting recombination in this nearby underdense region. So because of this, what you'd really need to do is you would need to, in full generality, couple the radiative transfer Boltzmann equation across the Lyman-alpha line to compressible MHD simulations. And that's not feasible. So we need a different way of handling the fact that we now need to account for this non-local radiative transport. So in our work, people have thought about this, other people have started to think about this as well, but in our work, our approach has been to try to build a framework in which we can handle this as kind of self-consistently as possible. And it turns out that if you'll permit me to sweep under the rug in what I'm doing this perturbative expansion, but if I can do a perturbative expansion in my free electron number density, that we can have full control over this non-local recombination process. So here I'm writing the free electron number density as some background rate, some linear perturbation, and a second order perturbation. Then if we want to know what the shift to the background recombination rate, we're going to take a spatial average. The homogeneous one just is what it is from your recombination framework. The linear one necessarily vanishes. So what we're after is the second order response, which will give us the perturbation beyond the background rate. Now, the details, again, I won't go into all of them, but what it involves is here I show you the recombination through the Lyman-alpha channel, which is what primarily drives primordial recombination. And it depends on parts of your phase space density. And so from this equation, you can see that if we're going to second order, what we'll need to do is we'll need to solve for the spatially averaged second order line averaged monopole and the equilibrium phase space density. So those are the components of the phase space density that we'll need to solve across the line. And in order to do that, this was first done in a paper by my advisor and Chris Arata in 2015 in the context of scalar perturbations to linear order. We're going here to second order to get these pieces of these guys of FEQ and F00 bar. So what first has to be done is it has to be solved to first order across the line for all Fourier amplitudes and for all angular orientations, so not just the monopole, because all the first order ones can source the second order part of the Boltzmann equation that we need to solve. And so that's what we've now developed on the recombination side and is fully under the control. Now we can solve for the pieces that we need to solve for this second order term that gives us the shift to the background recombination rate. I probably should have said this before, but also feel free to interrupt at any point if there are any questions. Okay, so now we understand the task at hand. We understand what's needed to be done. Before I go into, we need to shrink the co-moving sound horizon. We're introducing inhomogeneities. We now have a framework for computing non-local recombination in the context of these inhomogeneities. Before I go into the types of inhomogeneities that we would expect from primordial magnetic fields to source, I thought a comment was probably warranted on why primordial magnetic fields are taken seriously and are interesting to consider. So for a long time, they've been thought about because they come up in natural extensions and beyond the standard model and baryogenesis scenarios that people consider. But those also are from all the different from all those theoretical considerations, you really can only set an upper bound. The really big result came in 2010, though, in looking at spectra of blazars from Fermi, in which what was expected was you expected to see, with respect to the intrinsic spectrum, you expected that the highest energy portion of it, the TeV portion of the blazar spectrum, to have a suppression in that portion of the spectrum, because what was expected to have happened is these TeV photons would scatter off of extragalactic background light, leading to pair production. And then these E plus E minus pairs would inverse Compton scatter off of CMB photons and give you a secondary GeV emission. So what was expected was, with respect to the intrinsic spectrum, a suppression at the TeV, but then an enhancement above at the GeV. And instead, what was seen here, the intrinsic spectrum is this line. And what was seen in the data was the suppression and the TeV portion as expected, but then none of the enhancement in the GeV, in the secondary GeV emission that if this picture is correct, was expected to be seen. So there's different ways that people have considered to try to account for this, but it's most naturally explained by the presence of magnetic fields kind of permeating with large coherent scales that are deflecting these E plus E minus out of your line of sight, and therefore you're not seeing the secondary GeV emission. And people have tried to see whether these can be generated astrophysically. It's pretty difficult to go about doing so, though there's recent work and people still considering whether getting the required field strengths and coherent scales to explain these observations is possible. But this led people to realize that if they could be generated primordially, then that would naturally explain their presence and their large coherent scales and explain these observations. So this is the only lower bound that's set. It's roughly at 10 to the minus 15 Gauss at an integral scale of around a megaparsec is the constraints that you now have from the non-detection of these secondary GeV photons. Okay, so now let's turn back though to recombination, and let's hone in on primordial magnetic fields. So again, for the purposes of our work currently, we wanted to really cook up a context in which everything could be done as self-consistently as possible. And because we want to do this perturbative treatment, what we wanted to be able to utilize was work done over 25 years ago now, which used mean field theory, linearized MHD-like approaches to take this nonlinear portion of the Lorentz force, B cross del cross B, and break it down into portion that's a homogeneous mean field B naught cross del cross a small perturbation. And that is most reasonably done if you have a separation of scales in the spectrum of pure primordial magnetic fields. So you can break it down into this large scale mean field whose amplitude is much bigger than the small scale perturbation, but is spatially homogeneous on the scales at which you're looking, and also which you would want to not be time evolving, so that it neither rotates nor changes its amplitude. Now, the most conservative way that we went about trying to realize a spectrum that could be reasonably decomposed like this is to, if I parameterize my power spectrum of the primordial magnetic field as K to some spectral index NB, well, if NB is -3, that would be a perfectly scale invariant spectrum. So we're looking at spectra which are tilted redward from scale invariance. So that's with epsilon less than 0 under this parameterization here. Then I have power concentrated on the largest scales. So I've satisfied the criterion that I want B naught to be much stronger than the small scale perturbation. I can also set it on a scale where naturally this large scale mean field will be conserved. So that's another compelling feature of parameterizing like this. Massive caveat, this is a very constraining set of spectra, not ones that people who work on genesis mechanisms, I think, really take seriously. But again, the idea here was to try to put together a context in which everything could be handled as self-consistently as possible. And then at the very end, in just a couple of minutes, I'll comment on how this can be extended. Because we have a tilt redward, we have an IR divergence as k goes to 0. So we'll also need a cutoff scale, which will be the scale at which power is most concentrated, because we just have power running off to smaller scales. So this here I refer to as k lambda, the IR cutoff scale to regulate the divergence. Okay, in the last couple of minutes now, I'll just present very briefly the evolution, the linear MHD evolution, and then the actual results for the modifications to the recombination history, and then I'll conclude and comment on future steps. So the two key regimes that the fluid undergoes in its evolution in the early universe that I want to talk about are: the first regime is when the wavelength of your mode is larger than the mean free path of a photon. Then Thomson scattering keeps the baryons and the photons tightly coupled, and they can be treated as one fluid. If you're, though, in the regime in which they're tightly coupled, you now have the pressure support from the photons, and the relativistic equation of state, the CS squared is like 1/3, means that you have huge amounts of pressure, and the Lorentz force for reasonable field strengths is not going to be able to compress the fluid. So initially you have incompressible MHD, and in order to modify recombination, we need to source clumping. So the way that ends up happening is eventually, if a mode falls below the mean free path of a photon, the fluid now is one of just baryons with this background of free streaming photons giving you a viscous drag, but you lose now the photon pressure support, and the pressure is just set by thermal baryonic motion, which is much smaller than that the relativistic pressure from the photons, and now you have a chance to compress the fluid. So the standard picture you have is here. This is in the MHD context. These are fast magnetosonic waves. They're compressible ones. If you're above the mean free path of a photon, you're in the tight coupling regime. Basically, on all the small scales that we're interested in, these are all going to get damped away, and so you have incompressible MHD. But these this red band here is for transverse modes, or ones that are transverse in the tight coupling regime. Some of them get damped away as well. Some of them are able, though, to become overdamped and then survive into free streaming. And then we're interested in the modes that can start to become compressible near the time of recombination. There's much more to be said about the linear evolution, but I think I'm running out of time, and so I just want to get to the main results here. So when it's all said and done, you take care to evolve through these different regimes in the linear MHD context. You can then find all kinds of relevant quantities. The first one is, this is the dimensionless power per log wave number for the delta rho baryon over rho baryon, so the inhomogeneities in the baryon density field. Just point out a couple of key features. Here it's plotted for different field strengths as a function of redshift for different colors. 1100 again is near recombination. And I just want to note that as you go to weaker field strengths, the clumping scale moves to smaller scales. As you go to later redshifts, the clumping moves to larger scales for any particular field strength that you look at. And obviously, if you want to accurately model recombination, you need to have a reliable model. But I just want to point out here that even if you wanted to accurately capture the clumping of your baryons, if you have different models of recombination, you'll get an inaccurate account for the clumping. And one way to understand that is that in Saha, we saw recombination happens much faster. So you lose your free electrons, which contribute to the thermal pressure of the baryons. The CS squared falls like 1/2 very quickly. So there's less pressure support. So you get additional clumping in a model like Saha beyond the 3-level atom, which thinks recombination proceeds faster. Okay, I'll just wrap up with this slide, and then I'll conclude. So you then want to take everything you've done here, you've evolved all your linear MHD modes, you've coupled it to, near the time of recombination, the full radiative transport treatment to get the non-local recombination. And then you can make plots like these. On the left, this is the shift to the recombination rate with respect to the background. So that's really what you're after. On the left for a fixed spectral index and varying magnetic field strengths, and on the right for a fixed field strength and varying spectral indices. And I'm showing you 3 different ways of computing the shift. So dotted is where you're using local Saha. Dashed is where you're using the 3-level atom, but you're still just in any patch doing a local recombination computation. And then solid is the full computation where radiative transport is taken into account. You can see that even though you had less clumping in the radiative transport case, that you get a boost in the amount of successful recombination beyond the background rate over Saha. And that can be ascribed to the fact that when you allow for these non-local effects, the overdense regions where you get the most recombination happen, you allow Lyman-alpha photons to escape out of that patch. And so you allow for more successful recombinations beyond any local account of what might be occurring there. Okay, so with that, I'll wrap up and I'll just leave you with my conclusion slide, and I'll make just two comments on kind of future directions. The first is that this mean field theory approach might have applications beyond this narrow and admittedly very much toy example like spectrum that we've considered. So this was all for the purposes of just fully trying to get it all down, all the aspects that one would need to have a detailed and accurate account of recombination. So now trying to think about, okay, this is proof of principle computations complete. We hope to have it up on the archive in a week or so. Let's try to extend it to other contexts and be a bit more bold in its application. The other thing that can be done, though, is on the recombination side of things, handle things linearly and to be able to solve the radiative transfer Boltzmann equation. But on the MHD side, you need not linearize. You can imagine coupling the linearized recombination side to a full compressible nonlinear MHD simulation and just adjoining those two. And that would be compatible so long as you're not sourcing high nonlinear fluctuations. And people who have tried to run these early universe compressible simulations, some find nonlinear perturbations, which would fall out of the purview of this approach, but there's a bit of disagreement as to how nonlinear you would expect. There might still be a large region of parameter space for which that hybrid approach would be applicable. With that, I'll conclude, and I'll be happy to answer any questions. Thanks.
Thanks. So, are there any questions from the room? Experts, non-experts. Well, what? No. Okay. Yeah. You need to speak up. No, I think this one is good enough. We want to go first. No. Just agree and speak up.
So, thanks for the seminar. So, is a technical question. You consider spectral indices which are red, for which you have infrared divergences when you have perturbations. So, do you plan to have in the next coming result also the other spectral indices, like the blue ones considered by Karstad-Jedamzik?
Yeah, so for what is going to appear shortly, it's just the red ones. I should emphasize that even though the power in the magnetic field is concentrated on these really red large scales, the natural scale at which you source clumping, even for these spectra, is still very small. So it's still somewhere from 0.1 to 10-ish kiloparsec. And so we're still capturing a lot of the relevant features for, we think, the scales at which you expect to source clumping. Like this is similar to the scales that Jedamzik and others who work on this see for where they source their compressional power. But I think now to answer your direct question, for this first work, this is just going to be for red tilted spectra. So it won't be an apples to apples comparison with Jedamzik, but we do have things in the pipeline to now hopefully extend it to allow for more direct comparison to their work.
Okay, thanks.
Thanks. You show that there is this degeneracy between the primordial magnetic field and the level of clamping, baryon clamping. I'm wondering if you have any independent estimate of a baryon clampiness, or if there is a way to break this kind of a degeneracy between the two quantities?
So tell me if I've understood the question correctly. You would be able to, if you were to just be handed some matter power spectrum with excess power on these small scales, that would not necessarily indicate that there's primordial magnetic fields. There might be some other mechanism for it. And so might there be some other feature that one could point to that would say, no, these originate from primordial magnetic fields in particular? Is that right? So that you're not. Yeah, so I think that if we had a really fantastically understood models for the types of clumping that's on these small scales, and then we had some probe of it, like what some people look at with the Lyman-alpha forest, then one could argue, the exact types of features of the matter power spectrum on these really small scales. It's hard to find any other mechanism that would generate it beyond primordial magnetic fields. So if you were able to maybe get into the fine details of what's giving rise to it, but otherwise, nothing comes to mind immediately just from looking at the matter power spectrum. If I had a bump and someone said, I have this generation mechanism for what gives rise to this excess small scale power, and I were to claim, no, it's primordial magnetic fields, you would need some additional, I think, probe to be able to say, no, these originate from primordial magnetic fields specifically. So I think something like the Fermi data would be a way to break it. If you could compellingly make the argument, we need this field strength to observe to get the blazar observation. So these are probably originating from primordial magnetic fields. That would be one way to strengthen the case, but otherwise it's difficult to just argue if excess power is seen down there that it must have come from primordial magnetic fields, especially if you have another viable mechanism for getting that power.
Thanks.
Okay. So even in your highest magnetic field case, you are finding amounts of clumping factor which are a few orders of magnitude below the Jadamtic paper, say, right?
Yes.
And at the moment, your best explanation is that you have an incompressible approach, if I understood correctly, or let's say,
I should.
Yeah.
Sorry, I didn't mean to cut you off. I should clarify. So, it's not incompressible. This should be in the linear context, the full computation. It's mostly, it just happens to be, no worries. It's mostly incompressible for most of its evolution. But then even Jadamzik is looking at redshifts near recombination, like his compressible simulations start at 4,500 and then run through a recombination. The reason I think to not be too concerned with why this is so small is because we're looking at nanogas to sub-nanogas field strength, so in the ballpark of where Jadamzik's looking too, but all our power is sitting at the mean field super horizon scale. So the amount of power that's actually sitting on the kiloparsec scale where the action happens, where you expect to get this clumping, is much smaller. So this is several orders of magnitude smaller. So I wouldn't say that, I don't think that there's any way to say that this is incompatible with the Jadamzik result. We wanted a very modest clumping factor in particular to be able for this kind of fully self-consistent recombination computation to proceed as smooth as possible. There's ways to turn up this power just by moving the integral scale inward, moving it inside the horizon like Jadamzik looks at, and by changing the spectral tilt as well. So I would say that I would just describe this to the type of spectra that we look at, which again was cooked up to make the linearized treatment as simple as possible, and we were being very conservative with it as well.
Okay, thanks. So unless there are questions from the remote audience, I think I don't see any. I think this is it. Okay, thanks a lot.
Yep, thanks very much.
Thanks for the very early wake-up call. Okay.
Sure, it was a pleasure to join.
Take care. Bye.
Thanks.